Welcome to this quantum security and defense presentation. Enhancing AI with quantum computing for aerospace data analysis. And thank you for being a valued member of our community. Akshat Tandon is an AI researcher and leads the activities related quantum machine learning QML at Airbus Central Research and Technology. He leads research projects related to quantum machine learning and applies it to solve the company's challenges. His contributions span various areas, including computer vision, graph neural networks, multi-agent reinforcement learning, and swarm robotics. Akshat completed his master's degree in intelligent systems with a focus on AI and robotics at Cluster of Excellence in Cognitive Interactive Technology, Bielefeld University in 2017, providing a strong academic foundation for his work.
Thank you so much, Anna, and thank you so much, QSEC Dev team, for giving me this opportunity to show people here today the work we do here in Airbus related to quantum computing and the work especially focusing on enhancing AI with quantum algorithms for aerospace domain. So again, hi everyone. My name is Akshat Tandon, and I lead all the activities on quantum machine learning topic in the central R&D of Airbus. So, but before we move into this topic itself, it's essential to understand three key points: how and where QML or QC as a whole fits in within Airbus, within all the activities of Airbus. Why QC is or quantum computing could be crucial for aerospace use cases or application, and why should we think about enhancing AI with quantum computing? So, to answer the first question, we all know quantum technologies are transversal technologies, and thus Airbus, we in Airbus we are actively exploring all of its pillars: quantum computing, quantum communication, and quantum sensing. So not just quantum computing, but in all the pillars, and we are actually contributing to the critical infrastructure in all these pillars as well. To understand why quantum computing is crucial or could be crucial for us, it is important to also understand the role of high computational requirements for aerospace domain. So just to say that in as an example, like today planes are not just some mechanical parts that are flying together. They're much more complex. There's much more data rich and data dependent in the world today. Deals with huge amount of these data and to process them as well. Thus, to enable these kind of necessary high computational power, we in Airbus already operate a very high and very powerful HPC system, and we are conscious that those classical computing system may reach their limits in the future, and thus we are exploring or investigating different solutions to extend those HPC toolkits for ourselves, which includes, of course, exploration in quantum computing. Our KPI here is that we can apply quantum computing for relevant applications in our operational environments for our products as well as for our customers. And what are those relevant applications? We structure them basically in four problem domains or let's say use case families that where each or application basically in each family will basically be sharing the solution space or solution methods basically. First one that you see, first use case family that you see is the quantum simulation, which deals with all the applications related to, let's say, chemistry simulation or some other system simulation application. The second domain is quantum optimization, of course, uh, which can include use cases or applications in aircraft fleet optimization, satellite mission planning, etc. Then there is quantum solvers, where we try to find quantum methods to basically improve CFD simulation, for example. And then there is quantum machine learning, where there are various use cases, a lot of them, and of course, we'll talk more in detail about it in later on in the slides as well. Here you can also see some of the example applications in each use case family where we collaborated with external partners, industry partners, to explore the advantages of quantum computing in those specific applications. Of course, there are many more, given quantum computing is also still in comparatively in an earlier stage. So the best and the fastest way we realize is it to understand its potential is to collaborate with the quantum computing community to explore these application areas and the advantages of quantum computing algorithms. So with this in mind, we in December 23 we launched a Airbus BMW Quantum Computing Challenge. I hope many of you might have already heard about it. This was in partnership with AWS and was hosted by Quantum Insider. Together, we invited participants from all around the world to submit their proposals on um, application of quantum computing to the real world applications, so real world industrial applications in the area of mobility. So not just toy examples, basically anymore. And the challenge was basically divided into 5 tracks in both forward and reverse category. And in the forward category, if you see like the application use cases belong to one application use case belong to one use case family that we saw before in the previous slides. So for example, from smart coding belong to quantum simulation use case family, and you can also see like in in enhanced autonomy where we focused on quantum enhanced generative AI or quantum machine learning over there. And then the reverse track was dedicated to discover a new golden app for quantum technologies. Here, the idea was to ask the participants to submit some solution to the problem that they feel are going to be critical for us, and where quantum computing can be a good solution or can have a potential advantage. In the end, we had numerous application submissions from various parts of the globe. We shortlisted also 15 finalists after the phase one. And then in the end, for example, these are the five finalists that won the actual challenge in all the five the categories or the tracks that we discussed about. Here you can see, for example, Condela won the challenge in QML track with its innovative solution to generate critical test scenarios images for both automotive and aerospace domain. One which is one of the very critical application of even classical AI in aerospace sector. But as I mean, as this use case, like in the challenge that we gave, there are many other basically in the aerospace industry. And just to give you a glimpse of where classical AI uh, can provide a lot of advantage for some of the problems or challenges that we have from or by analyzing the data that we have in the aerospace domain, for example. So here are some of the examples. For example, over here, for example, you can see on the right side one image basically showing maritime activity of the globe. Of course, AI is used and can be used potentially to find abnormal behavior of vessels on the sea. On the right side, for example, you can see like AI can also be and is currently also used to detect defects in 3D printed parts. So given all these possible potential application of classical AI for aerospace domain, we must ask a question: why should we think about enhancing it with quantum? So of course, these are like the classical AI has potential to solve many of these challenges, but they often reach their limits in terms of the amount of data they can handle, the complexity of the model that they can learn, and of course to the time of like even related to the computational speed of these algorithms. So as we see with LLM, for example, the as soon as these models will actually become larger and larger, there will be also questions about sustainability and how much power they consume. So of course, one of the possible or potential solution could be to explore quantum enhanced AI solutions, meaning to say um, we can try to solve these current challenges associated with classical AI with enhancing them with quantum, and try to solve those challenges related to classical AI field. And there is a lot of research. Various research already show some potential advantages of quantum AI. For example, some quantum enhanced model can learn more complexities with even reduced number of trainable parameters as compared to their classical counterparts. So given this potential of quantum algorithms to deal with large amount of data set and solution, and also in terms of their speed, it could be explored and it should be explored. So with this in our mind, we collaborated with QCware to find a quantum solution for the maritime use case that we discussed about in the previous slide. Here, the image basically shows the trajectories of all the ships in a specific geolocation. And the idea is basically to use these images to predict whether there's some abnormal behavior of the vessels or not. We collaborated over here with QCware to develop this kind of an anomaly detection algorithm, therefore. A typical solution for a classical solution could be basically an autoencoder model, where we train the model to first learn a low-dimensional representation of these normal or non-anomalous input images, and then we use this low-dimensional representation to reconstruct the image back. So if during the prediction or inference phase, if the image has no anomaly and it's a normal image, or it's an image with normal activity, the reconstruction error is going to be nearly perfect, and the reconstruction error is therefore going to be pretty low. If the image has an anomaly, the reconstruction of this image is not going to be perfect, and of course the reconstruction error is therefore going to be higher, because the model never saw and learned to encode that anomalous part of that image, basically. And therefore we use this autoencoder, classical autoencoder model, and converted it to a hybrid quantum classical encoder. And what we did therefore is we we basically implemented a quantum enhanced convolutional neural network circuit, where we basically used this kind of a pyramidal structure circuit, which was made up of RBS gate. So RBS gate is a reconfigurable beam splitter, and this is basically inspired from the work which was previously done by QCware already. This circuit is good in the sense that only possible state that this circuit results into is only all the possible orthogonal state, which is in some sense analogous to a less costly quantum enhanced orthogonal neural network. An orthogonal neural network are good in the sense because they reduce the requirement of trainable parameters, and also reduce in these circuits, for example, the risk of barren plateau. And with this circuit, we trained this model, and we basically ran it on test time series data. So here you see as an example of one of these time series data where we tested this algorithm. The results showed that the quantum enhanced models was not only able to detect anomalies that were detected that were not detected by the comparable classical solution, but they also seem to be more resilient to the noise in the data. But still, there were certain anomalies, artificial anomalies, that were not detected by both classical and quantum solution. And to improve that, and to improve our quantum models further, we wanted to see if quantifying the confidence of these predictions by this model would help us. So with that in our mind, we basically moved towards Bayesian neural network, basically, which means that instead of learning point estimate of a weights as in a standard neural network, we learned the variance or the distribution of the weights, enabling us basically to sample, let's say, 100 weights out of this distribution, and which can further be analyzed to basically analyze the variance in the model's prediction, which in some sense relates directly proportional to the confidence or the confidence of the model, or can help us quantify the uncertainty. In classical BNNs, and like we can, it's already difficult to basically have a very good quality model learned using Bayesian neural network. There's some challenges over there, but adding to that, if you want to actually add the the orthogonality aspect also of the weights, or the orthogonality constraint on the weights as well, it becomes even further more expensive to do that, because after every sampling you have to orthogonalize this sampled weight matrix in classical domain. But sorry, oh, sorry, but basically the distribution but in quantum enhanced orthogonal CNN circuit, this pyramidal circuit that we saw before, if we learn the distribution of parameters of this RBS gate, this again of course is less complex, less expensive, but we end up having always a weight sample which is always going to be a like a matrix which is weight matrix which is always going to be orthogonal, which basically results into a better estimation of uncertainties of the predictions from the model. So in conclusion, we see that quantum computing is a promising candidate for many aerospace applications and use cases. QML solves in many cases and provides better solution for some of these applications as compared to its classical counterpart. The Bayesian neural network we observed till now, like with our experiments till now, the quantum enhanced Bayesian neural network also gives us higher confidence for right predictions as compared to its classical counterpart. So there's also some potential over there. And yes, Airbus right now does and will continue to partner with the best in the industry to further drive this innovation in quantum computing and quantum ecosystem as a whole. So with this, I would like to thank you all, and I'm open for if you have any question.
Thank you so much, Akshat. This was great. I already have some questions. Let me make sure that I didn't miss any. I just copy them to a main chat for you. I think I got them now all.
Oh, you're sharing where exactly?
In the chat.
In the chat, okay.
I would hope so. That was my intention. So if I'm copying them back to the people that send them to me, then please let me know.
Okay, so I see one question by Wim. Do you consider quantum annealing for optimization use cases? Yes, Wim, we do. Um, uh, yeah, we have explored that option as well. So yeah, there is already some published material on that. I can share with you as well later on.
Then there was a question from Alain. Would you please share references to your work with QCware around applications of quantum machine learning?
Yes, so for that we are in process of writing a paper, and we will soon publish our work on this project itself on orthogonal Bayesian neural network. So you will soon have it with you. So yeah, for sure it will be publicly available for everyone.
Then we have a question from Bill. If you see, where do the data sets from your LLMs come from? Are you treating each? And then as IoT points that log the anomalous activities.
So this is not an LLM model, just to clarify. So it's not a large language model that we're talking about. With the anomalies, yes. So what happens with this autoencoder structure? The benefit of that is that you only train the model with normal or mostly normal data, meaning non-anomalous data, and thus you assume that the model is able to perfectly reconstruct normal data. But and whenever there is an anomaly, so then because the anomalous feature of, let's say, the image in this case is not learned to be encoded in the bottleneck part of this model, the reconstruction of course will not be possible therefore. So thus saying it like this, like you don't need to label anomalies in the data in that case. So you just need to feed this network with a lot of normal time data set, basically. And it should be able to ideally predict anomalies over there.
Okay, I'm going to read you the next question from Annoy. Microsoft and many others are exploring a workflow where they are integrating HPC, QC, and AI. Does Airbus also explore similar workflow where strengths of each is explored to reduce overall underlying infra for AI?
Yes, all these aspects are also being explored for some time now by Airbus as well. So yeah, we are actively looking into how quantum computing as a whole can be integrated with the current HPC set, and can also be used further to enhance and improve the computational aspects of current classical AI models. Is there sorry?
Yeah, there is a next question from Amara. Is there a research paper for the AIS maritime research?
Yes, actually, there is a research paper in the classical domain, and from our side, it will be soon coming out as well. So, with the quantum enhanced solution. Um, I think that answers. If you mean in the classical domain, yes, there are many actually paper which do that using the same methodology that we discussed. In the classical, in quantum hybrid domain, uh, there are not many explicitly for maritime research with AIS data.
Actually, I have a question maybe because it's another research paper that we are having question about. Where will you be publishing? Is that something that you'll be announcing also on Airbus page, or where one can look for the
No,
papers?
sorry. Yeah, so we are planning to publish it in some conference, public conference, so that it's easily accessible for everyone outside even Airbus. So not just internal publishing, we're talking about more external communication.
All right. And then we have a question from Rayesh. Can you share insight why BNN works well with a pyramidal structure of quantum circuit? Is there a hidden insight into the structure?
Yes, in the end, thanks Rajesh for that question. Actually, that's a very interesting one. So the RBS gate, you are actually, so if you look at the RBS implementation with these universal gates, you can actually see that you basically trying to learn just the let's say Gaussian distribution of the angle of this gate, which basically means like if you're using let's say 3 of these RBS gates in your circuit, a minute change in this angle actually results into a very huge difference in the weight matrix as an output after this operation, or like the operation on the input, let's say state. So meaning to say like if I say it in quantum to classical analogy basis, a small variation in your theta value over there results into a very huge diverse weight matrix, which is also orthogonal in the classical domain, let's say. While on the classical side, they're always going to be just like a Gaussian distribution of Bayesian function. So basically, uh, it's comparatively much more diverse weight matrix with each sample if you use RBS over there. Plus, also it's easier to train them as compared to BNNs in the classical domain, because all these methods, variational inference, for example, they always lead to some kind of a suboptimal solution usually. So that's another advantage. I hope that answers the question.
It seems so. I think we covered a lot of questions. So thank you, Akshat, again.
Thank you for watching this presentation, and thank you for being a valued member of our community.